Anyway, so today we're going to pick it up where we left off with trees. So this is our first recursive data structure. Hold on. Right. So this was our first recursive data structure, and we can start again with a abstract data type, a functional specification of what operations we expect out of a tree. And so the idea here is that a tree is something that includes a tree, right? So for a binary tree, that means your left child and your right child. So every binary tree has two trees underneath it, essentially. And so we can create a new tree as a value and the two trees that are underneath it. Now, we have to stop somewhere, and so we need a notion of an empty tree, right? And so that's that first constructor, new empty, and that also produces a tree. And an empty tree is a tree, it just can't have anything underneath it, and but it is going to implement this interface, right? It's just a different implementation of the interface. That's the way to think about it, right? We have empty tree, and then we have a non-empty tree. So then, so we can get the value and set the value and get and set the right. This is just basically an open data structure. We're allowed to play with any of its component parts. We're providing getters and setters for everything. And we had a few notions about how to measure a tree. One of the things we talked about was the height. So from the node, the root node of any tree, all the way down to the furthest leaf. And so that's there too. Once we put things into a tree, then like a list, we might want to say, go find something that was in the tree, like is something in this data structure. And so we have a contains method. And then, we don't absolutely, an ADT only, in the end, really only needs the canonical operations and then a few basic, how to get to the data operations to be useful. But often we include other useful things that technically don't need to be there in order for the ADT to work, but are nice functions for them to have. So, for example, a quick and easy way to check whether or not a tree happens to be an empty tree or a non-empty tree, right? So, again, we start with which ones are canonical. Those are the ones we need in order to be able to create any possible version of the tree, right? Well, if we need the empty tree because that has to be the tree at the bottom, right? That's going to be our leaves. In some implementations, in other kind of data structure textbooks or things that you might see online, they might use the value null instead of us having an actual empty tree. But I'm doing this for a reason, because using null as something to signal something inside your data structure is really usually a cop-out, usually something where if you just took the time to do it right, you'll reap some benefits. And I'll point a few of those out here. So the way to do it is not to have null as some special value, but instead to define the idea of an empty tree, right? And so in order to create a leaf node, like something that's at the bottom of a tree that doesn't have any more trees underneath it, you create a new tree, and then you just give empty tree as the two leaves, right? That's how you create a leaf. And then if you want to create, some other node that has, subtrees underneath them, then you can, again, use that normal constructor for, taking a value and two subtrees and turning it into a new tree. All right. So, so then in order to think rigorously about our data structure, we want to make sure that we have some notion of correctness, and it helps to do an axiomatic specification, right? Okay, so we have to do an axiomatic specification on the two canonical operations, creating an empty tree and creating a non-empty tree. And so we'll start with the empty tree, right? The empty tree constructor. And so we basically do a cross between all the non-canonical operations and the construction of a tree through one of the canonical operations. And we see, for an empty tree, it's pretty easy. Everything's undefined, right? And that's okay. I mean, technically, that's a little, that's a cop-out. But not a cop-out. I mean, that's unfortunate, because now we have this special undefined. Like we have to somehow model undefined. In Java, we do that with an exception, right? That's okay. And so we have a tool for that. But there are some things that an empty tree can say, right? And that's the reason why you should use a special empty tree type instead of null. Because we do know that an empty tree doesn't contain anything, and so it doesn't matter what you ask us to look at. I'm missing a parameter here. Contains needs to take a value. Sorry about that. Right? And so, you know, that's not for nothing, right? That can be a useful operation. And we'll see how and why. But is empty, that's a useful thing that a tree can say. An empty tree can answer that question correctly, right? Now the other one is obviously more interesting, right? So we take our non-empty tree constructor, which takes a value, a left and a right, and we cross it with all the non-canonical operations. And so if we create a tree with a particular value at the top, as the value at the top root node, then we, and we get the value from that tree, we get back v. That makes sense. If we set the value of a tree to be something new, v star, then that's the same thing as just creating that tree directly. We didn't have to, and so we're able to show that. And then, getting the left, setting the right, getting the right. All of these axioms are pretty easy to kind of see. And now we see why having an empty tree type helps us. Because when we get to contains, where we say, oh, do we have a v1 inside a construction of a tree? The nice thing here is that we can define its axiomatic specification. The equivalence is essentially a recursive call for finding v1 on the left-hand side or v1 on the right-hand side. Right? I mean, I know v1 doesn't equal v2 because I use different identifiers. The v1, looking for v1 in something that starts with v1 obviously is true. But the point is that when I'm looking for something that is not at the root, I can recursively define it as, well, it might be on the left or it might be on the right. So look there, and if that's true, then great. And if it's false there, then look on the other side. And if that's true, it's great. And otherwise, if it's false on both sides, it's false. Right? This tree does not contain that value. We can't do that like as rigorously. I mean, not rigorously, as exactly. Like if we had an undefined construction for for null, right? So if we had to worry about the leaf, right, getting to the bottom and then calling contains on something that doesn't exist, right, then we have to, it becomes a lot harder to provide this axiom. But this works nicely because when we get to the bottom, we're going to get to an empty tree. That's going to be what's at the bottom underneath the leaves. And sure enough, empty tree says, oh, that's defined. It's well defined. We have an empty tree constructor, and the contains on an empty tree is, in fact, false, always, right? And then, of course, a non-empty tree would always say false for being is empty. So that's motivating why you generally don't want to use null as sentinel values in data structures, and although you'll see it done all the time. All right. So, I mean, there are reasons. I'm not saying there are no reasons. Like, they have to do with the fact that you can save some memory, but usually it's not saving enough memory to make a difference, right? All right. So, now, that prior slide had all of them except for height, right? Here, we're going to have a problem. It relates to the fact that empty tree is undefined for height, right? Because there is no height for an empty tree. So now we would like to be able to recursively define the axiom for what is the height of a tree I construct with this constructor to be, well, it's the maximum of either its left side or its right side plus 1 for this, this node here, right? That would be a very convenient and easy way to define this axiom. But height of the tree is not well defined for certain constructions. In fact, height of new empty is undefined. And so we have a problem here, right? We have to solve it somehow because this is not always true. So we can do one of three things. We can rewrite the axiom, replacing all of these L's and R's, right, the actual tree, with all the combinations of the canonical constructors that could possibly occur. That's one thing we could do. The other thing we could do is we can have a more sophisticated axiomatic statement, or axiom, right, that expresses that right-hand side as a piecewise function where we make sure that all the pieces cover the domain of the function. Or we can get clever, right? So we'll see it in all three ways, right? If we're going to rewrite the axiom with all the possible canonical construction patterns, basically we take the axiom left-hand side and we create 4 new axioms where instead of having L and R as placeholders that could be any kind of tree, we put in all the combinations of the 2, in this case, canonical constructors that it could be, right? So we're allowed to use placeholders for the next level. That's okay, because we're just worrying about what it means to be a height of a tree, which, if we have an empty tree, is not defined. Once we have these 4 new and then we have easy ones for easy right-hand sides here, right? So for the top one, the height of a tree that has 2 empty leaves is 0. Yeah, 0, right? It's just a leaf. The root and a leaf, it's all one, and the distance between the root and the furthest leaf is 0. That's the same node, right? And then the height of a tree that was made with an empty tree and something that's not empty, well, I don't care about the side that's empty, so obviously it's just the height of what's on the right-hand side, and I can write that as the right-hand side. And the same thing for the third statement. And then for the fourth statement, that's where we can use the maximum of the 2 and plus 1. I should have used different placeholders for L and R here. So this should be like L1, R1, L2, R2. Or we could just still have the same left-hand side we started with, but now have a piecewise function. This is essentially the same thing I just did and rewritten in a different way, right? Now we have all the, I have, 4 different answers for what this function could be with the right-hand side, depending, right, on all the different combinations of various characteristics of L and R. If L is empty and R is empty, then it's just 1. Actually, that should be 0. I just figured that out in my head, right? So, et cetera, right? So really, this and this are just kind of different versions of each other. This one is 4 different statements to cover the domain. This is 1 statement, but you're just careful that you have all the pieces that cover the domain, all the possible combinations of the inputs that matter. Or we can get clever, right? Wouldn't it be very clever if we define the height of an empty tree so it's not undefined, so we get rid of the discontinuity and just call it -1, right? That actually works perfectly well, because now the height of any non-empty tree, and here it actually works, right, is the maximum of the left and the maximum of the right, right? Or maximum of either the left or the right plus 1. Right? We know that works for all the nodes in the middle, right, from the root down to where the leaves are, and it also works for the leaves. Because if you're a leaf and you have 2 empty trees as your children, then the maximum of -1 and -1 will be -1, and you'll add 1 to it, and you will have a height of 0. So a very clever solution. We just got rid of the discontinuity, right? Sometimes you can do it, sometimes you can't, but it can guide your implementation, right? Speaking of which, let's take what we know about trees from a kind of analysis point of view and go to the code. All right. So the functional specification, right? Remember what that looks like. That's the types that go into a function and what it produces, right? The kind of and the understanding of what that what these are supposed to do. That functional specification, that's our interface, right? So if we go to binary tree, right? There's our interface. And there are the types and the values. Now, when we do it in Java, the functional specification is purely functional, right? It assumes that the input and the output are completely different things. That you give me some input, and then I produce this output, which is the effect of this operation. But in an object-oriented point of view, our objects we're designing them as mutating things. In other words, I create it, and then I do things to it through methods, and it mutates, right? And so it is the thing I'm operating on. So that functional specification way back here, the one that's very abstract, like this thing, right? See how all of these operations, so we'll ignore the constructors for a second. That just constructs a new tree. But all of the operations take the tree that is the input plus other stuff, which is part of the operation, and produce either an answer or another tree, right? And so we can think of, right, all of the, that first list, that first parameter in the functional specification, that's the object. That's the this pointer when the methods are operating, right? Because I have to go through an object to get to the method, right? And so the object itself is that first parameter in that functional specification. Then the parameters to the method, that's the other stuff I need. And then if it produces an answer, that's my return type, right? And if it produces a change in the object, then the object mutates, and I usually have a void as a return type, right? And so then the output, any change to any of the functions that produce a output, instance of the data type based on the operation, right? That's these mutating methods that usually have void as their return type, because they're not returning a new tree, they're just taking this tree and mutating it, making it into its output. We lose the input, right? So whatever whatever version the input was is gone now because we've mutated the object. All right. So here is our functional specification, right? Get value, set value, get left, get right, et cetera, et cetera. We don't have the constructors here because that's part of the implementation of the class, right? So we don't declare constructors in the interface. Here is my implementation. It's going to be binary tree impl, right? So, and remember, so we want to do this generically. It's a binary tree of something. This is the value that we're storing at the nodes. And so here is a binary tree impl of something, right? And we can use that type. So each tree needs a value, a left, and a right. And here's the recursion, right? Or the recursive part of, it's not recursion because we're not actually in a function here, but the idea of recursion, you can kind of see it in the structure. Because a binary tree impl, right, which implements binary tree, includes binary trees as part of it, right? So here's the, right, so let's do the empty one first because that's super easy. Here's my empty binary tree. It doesn't even need a constructor because it has no fields. And everything is a runtime exception, except for height, which I've made -1 for our clever solution to that problem, right? And then contains and is true, which actually have real answers on an empty tree. And then my non-empty tree, which I've called binary tree impl, right, takes a value in 2 other trees and encapsulates that information and then implements things. Most things are pretty straightforward. Get value, set value. Get tree, get left, get right, set left, set right. And now I can test for null as an error, right? Because nothing should ever be null, right? No one should try to make this null. If this needs to be if you don't want any children in that direction, then put in an empty tree. But you can't give me null. I should have had some defensive programming in the constructor, but I did do it in the setters, right? Contains becomes pretty easy. If the element is here, and I'm using, in this case, the object equals method, right? So that way, if we have a more sophisticated version of equals for that kind of object, like string, then we can do it rather than saying double equals. And that works because every type has an is of relationship with object with a big O, and object with a big O is where equals is defined. And so, right, so if I found it, great. Otherwise, look left. If I found it, great. If I otherwise, look right. If I found it, great. Otherwise, return false. Now, this is a perfectly nice and perfectly readable. This is not how I would write this code. I would write this code, and you will too, once you get used to the idea, once you see these opportunities, is to write it as return, right? Either if element equals value, or if that's not true, left contains elements, or if that's not true, right contains element. And if that's not true, then that whole expression is false. Voila. See, look at that. Isn't that it's just pretty? It's just pretty. Just pretty. Gotta love it. All right. So, and then is empty obviously returns false. Okay. Okay. So, so that's a good place to take a breather and to talk about any questions. Well, first of all, any questions about what we've just said so far? Yes.
So, when on the first couple slides you had new and then 3 elements like value left, right, or something?
Yeah.
If you added a 4th one, where would that go? Because how do you know that the second 2 are the left and the right?
Oh, I just know it in my mind. In other words, I'm the designer of this data structure. I have an idea for what these things are going to do, right? And so, yeah, so, if somebody is giving you a functional specification, then they have to describe exactly what these, what the role of the inputs are, right? So if I was going to give you this and say, please, can you code up some code that implements this data structure, right? I would have to explain new empty creates an empty version of the tree, right? And new creates a non-empty version of the tree. The value is stored at the root of that tree, and the first tree is its left tree, and the second tree is its right tree. And I would say that thing, right? I would describe what I need this data structure to do and how it's going to work, right? Your job is to understand that. So there's already a sense like that you have been either described to or have created in your own mind an understanding of what it is that the data structure is supposed to do, right? And now here is the kind of the formalisms we can apply so that we make sure we have a good design and that we have an understanding of how, like a more formal understanding of what we kind of know in our head or we're told, and now we can write down more rigorously. Right? So at this stage, there's not a lot of information. It's still a lot in the person's mind who's reading this or writing this. Right?
How would you access the, like, for example, if you look for like the left tree or like left branch, that has a tree, how do you access the next level of that?
You can just the way you would, right? If you wanted to access, okay, so I think the very next set of slides is going to tell you exactly what you want to know. So I'm going to hold that off for a second. Yes.
Would it be a good idea to conceptually think of this as a linked list with 2?
Yep, you can think of it that way. So when we did a linked list for the list structure, one of our implementations was, a chain of nodes, right? So a tree is, you can think of a tree as a chain of nodes that starts at a root, and then instead of having just one place to go, happens to have 2 places to go, right? Or more, right? Depending on what kind of tree it is, right? If it's a binary tree, it has 2 places to go, right? And then, and then the next guy has 2 places to go, possibly, right? So we could, you get, this is a tree, actually. Funny enough, a list is a tree. It's just one that only has, a binary tree. It's the one that only has, one child ever, right? And these guys are empty, and empty, and empty, and empty. That's a binary tree, right? But it kind of looks kind of like a list, right? So, in that sense, they're very related. Yeah.
How would you use your contains function if the tree had more than just one branch to the left and the right?
Oh, that's the beauty of recursion, right? So when I implement this, right, here's contains, I first say, is it here? Is it at the top, right? And then I call, because remember, left is a tree just like I am, right? And so I call contains on left. So then I go, now I'm right back where I started, but now this points to left. And it says, is it here? No? Well then, look left. I'm going to keep looking here. Look, and this is the next set of slides. And so, and then I'm going to get to the bottom, and then it's not going to be at the left at the very bottom, and it's going to like come back and say, oh, well, look right. And then it's going to look right, and if it's a leaf, there's not going to be anything there either. And then it's going to go back to where it came from, which is whoever called left the time before it to get to that spot, right? So you'll end up searching the whole tree, right? All right, and in fact, that is the very next set of slides, right? Traversing a tree, right? How can you visit or process every value in the tree? Like, for example, looking for it, contains, okay? There are two basic approaches for how to search for things in a tree. One is naturally recursive, and that's depth first, and contains basically did that, right? And we'll see exactly how, and I mean, like, we'll revisit that in a second, right? And that's the idea of working as far down as you can until you hit the bottom, then coming back up and going the other direction, and then coming back up and coming back up and then going the other direction, and then down, down, up, down, like up and down the tree until you set every single one, right? So that's depth first, right? Breadth first is harder to do recursively. In fact, it's impossible to do recursively. Well, I don't know. Well, yeah, I'm pretty sure it is. But is more of an iterative solution, but does provide a different way of searching the tree. That's where I start at the top, and I call that level 0, if you will, and I start there. And then I look at all the nodes at the next level, and then under them, all the nodes at the next level, and then under them, all the nodes at the next level. That's, that takes a little bit of bookkeeping in order to do. Depth first search can be done recursively, like we just saw, but breadth first search takes a little infrastructure. In depth first search, we'll do that one first because it's a little bit easier to see recursively, which we just did. There is 3 different ways we could do this. We could either process the value right at the top first, then look left, then look right. That's exactly what contains did, and that is a depth first pre-order operation, right? I mean, a traversal. Or I can, move where I process the thing at the top. Or I could first recurse left, and then process the thing on the top, and then recurse right. That's in, no, I'm sorry. That's actually, what I just said is the last one, in order, right? And that kind of makes sense. Everything on the left of me, then me, everything on the right of me, right? And we're going to take advantage of that structure in a second. And then post-order is the opposite of pre-order. First do my left, and then do my right, and then do the value at this spot. So if I have a tree, then the pre-order depth traversal starts at the top and visits LO, and then it goes to its left child. There it starts at the top and visits OK, and that goes to the left child. There it starts at the top and visits YA, and then it does not go any further because there's an empty tree there, so it stops, right? R contains, it actually went to the empty tree, and the contains by definition was defined as false for an empty tree, so it just kind of comes right back up, right? So this is how contains would do this. Let's say contains is looking for MI. This is where we're at YA, right? Then we come back up to where we were processing OK. We already processed OK in the left. Now we go right, and so we're processing there. So again, we process RE and we go left, right? So now there's another call, another recursive call, and then now we're processing FA. We go left, and then we go to the empty tree and immediately come back up. We go to the empty tree and immediately come back up, and then back up to FA, right? Then down to ZZ. Then back up, and then down to K2, then back up. This is a more general tree. It's not binary, but right, et cetera, right? We can see a slightly different order, but the same idea in post order. That's just visit your children in some order before you visit yourself. And so obviously your children are ordered, right? And you can, of course, then have variants of this where the ordering of the children are different, right? Here there's a presumption that left comes before right, but there's obviously a variance where right comes before left, right? But there's some order to your children. It has to be consistent from node to node, right? And then post-order is basically like pre-order, and then in order, right, is, we do everything to our left first. The and then, so the very top of the tree ends up being in the middle of the output, right? So in pre-order, the very top of the tree is the very first thing. In post-order, the very top of the tree will be the very last thing. In order, the very top of the tree should be somewhere in the middle, depending on how many things are to the left and how many things are to the right. Breadth first needs a little infrastructure, right? You can't do it as recursively like we demonstrated with contains, but we can do it iteratively, almost like a for loop, right? And so in this case, we're using a while loop. So the way to do breadth first is you create a queue of trees, right? And so that's going to be the infrastructure you need. And you remember what a queue is. A queue is just a certain way of using a list, right? You can build a queue out of a list very easily. And there's two operations on a queue. You add to the queue, and then you take from the queue. And it's like a line, a normal line, first in, first out. So whatever got added first is the first thing that gets taken out when you dequeue. Okay? And so you take one of these, you create a queue, and then you take the top level node you have, like the tree, right? The tree you have, right? That you're trying to process in a breadth first manner, and you take that tree and you put it on the queue. And now you go into a loop. And while the queue is not empty, you take the next thing out of the queue, you dequeue, and then you process the value at the top of that tree, and then you retrieve its children. You take its left, right? You use a getter to get the left tree, and you put it into the queue. And you take the right, and you get it out of the tree, and you put it into the queue. You're not taking it out in the sense that it's still there inside the tree. You're asking for its reference, right? You say get left, get right, and then you put it into the queue. And now you're done with your while loop, and you go back to the top and say, is there something in the list? And if there is, you just repeat this process over and over again, right? What will happen is any tree that has children, when it's processed, will put either one or two children back on the tree. So the tree is either the same size or getting bigger. Any tree that doesn't have children, the leaves of the tree, will get processed and not result in anything being put on the tree, right? And since we're doing it by children, we'll end up slicing through the tree by level, starting at the root, then going to everything that was a child of a root, then everything that was a child of a child of a root, then everything that was a child of a child of a child of a root, right? Et cetera, et cetera. Right? So the breadth first search of this example starts at the top, LO, and then OK, MUHI, and we can see it even preserves the order as long as we are consistent about how we put things on the tree, right? We always put left first and then right. The children have an order. And of course, we could have some sort of reverse version where we do right and then left, right? The cool thing is that even though we can do depth first search or depth first as a recursion, we can also do it this way. And all we have to do is change it to use a stack instead of a queue, and now you're doing a depth first pre-order traversal. You can't do all three depth first searches this way, but you can do a depth first pre-order traversal if you simply do the exact same algorithm, and instead of using a queue, use a stack. Remember what a stack is. We pop and we push. We're basically adding and taking from the same side of the list, from the same end of the list. If we just use the exact same algorithm and kind of put and change the order in which we manage the children remaining to be processed, between a queue and a stack, then we take a breadth first search and we turn it into a pre-order depth first search. So there's something kind of deep between these two things, right? It's like the difference between a queue and a stack. They work in fundamentally the same way, but with just this fundamental difference where the queue is doing it where you add on one side and you take from the other, and the stack is doing it where you take from and add on the same side. The breadth first search goes in a particular order down level, and this depth first pre-order goes in a particular level down to depth, and the difference is embodied by this difference between how I'm managing the children. I actually think it's kind of cool. Maybe I'm thinking too deeply about it, but I don't know. Oh, I thought it was cool. Anyway, so a special type of binary tree. So that binary tree was kind of like list in the sense that it's a structure and it has well-defined semantics, but how I use it, whether it's useful to me, it kind of depends on how I use it and why I'm using it, right? And so there are, just like we might have sorted array in order to, or stacks or queues in order to optimize for certain operations and to kind of restrict the operations to a particular way of using a list, right? We can do the same with trees, right? We can use the idea of trees and binary trees, but then come up with additional semantics that prove useful. And one of the most useful structures is a binary search tree, okay? And so a binary search tree is just a binary tree in structure, right? There's no difference in how it works mechanically, but it now has additional axioms and methods and functions that do things particularly efficiently with respect to order. So again, now binary search trees can only be used with things that are comparable. I need to be able to take the values at the nodes and know which one comes before which one. And if that's true, then if we restrict ourselves to that type of value, then we can use a binary search tree to very efficiently store things in order, right? And so, now, by definition, every binary search tree is a binary tree, but the reverse isn't true. The reverse is only true if you are abiding by the binary search tree invariance. And so here's this word invariance again. It's what is always true, either at a step in the algorithm or for the state of a data structure, right? For a binary search tree, these things are always true. All the values in the child to my left are smaller or equal to the value that is stored at my root. And all the values that are in the tree to my right are larger or equal to than the value that I'm storing at this node. And furthermore, my left and my right agree to abide by these rules too. Okay? When you do that, when you add these invariants, right, then you get a different functional specification. It starts with the tree, but binary tree, but some things go away, right? What goes away? Set left, set right. That's no longer allowed, right? I don't know what kind of tree you're giving me, right? I guess you could change, or that you put it in the right place, right? So I don't want to allow that method anymore, right? I still want to be able to retrieve my left or retrieve my right or get my value, right? Right. And so I still might want the height. I still might want to know whether this tree contains stuff. But now, because this tree has to maintain the invariance, instead of having allowing you to construct any version with any old trees and change things around any way you want, like the original binary tree, now I can't let you do that. So my constructor, I no longer will construct a binary search tree out of parts you give me because I don't know if those parts work the way they're supposed to. I will let you create an empty one, right? Because an empty binary search tree, I know it's just empty, right? But so then you need to be able to create any binary search tree. So I'm going to give you an insert, right? You tell me to insert a particular value, and I will find the right spot for it and put it there, and that's how you can build your tree, right? And similarly, because you have no way of rearranging the thing, I'm going to give you a remove. You give me a value to look for, and if it's in my tree, I will remove it, right? So, right. And then, because it's a binary search tree, the reason for a binary search tree is to store things in an order. And so, I often I'm looking for the minimum or the maximum thing in the tree. All right. And that brings us to A5. You are going to implement a binary search tree. I have purposely not worked out the axioms for you. You don't have to. It would be a reasonably good exercise for studying for the midterm, I think, right? So I've given you the functional specification. I've explained the invariants that need to be true about this structure. I've explained with words, right, how these functions are supposed to work, right? And now you should be able to identify which are canonical and do the cross product and, and come up with the appropriate definitions for, right-hand side reductions for that combination, right? All right. Regardless, right? Here is a, your actual work, your assignment, is to implement this. Now, I've already started a lot of this, so just run through it real quick. This should not take that long, I hope, but I could be wrong. I've been wrong in the past. Let's see here. I need the assignment link. And then here's my GitHub. Here's the starter code. I'm going to clone it. I'm going to repo it. Sorry. Oh, it's already there. Oh, I need to go somewhere else. I'll go there. All right, and that Java project. Okay, so when you set up your assignment, you should end up looking like this, where we have A5, we have bst.java. That is the interface. That is the corresponding interface for that functional specification we just went through, right? So it only works for types that are comparable. We saw that earlier. We know what that means now, right? Because with a BST, we need to be able to know what's bigger, what's smaller, right? So use compare to when you're checking elements against other elements, right? Because that's the point of the comparable. -1 means whoever you called compare to with, right? Whoever's method it was that was compared to, that was smaller than whatever you provided as a parameter, right? So that's -1. 1 is the other way around. 0 means they're the same. Right. So then we have size, right? For size is like height, except it wants to know how many nodes are in the tree, how many things are in the tree, because the tree could have different shapes or whatever. It's not a formula of the height. You have to go out and count them, right? And then insert is if you give an element, then put it in the right spot. And remove, right? Now, here, this is important, right? For insert and remove, you'll notice that they return trees, right? So you would think that this would be a classic case of something that's in your functional specification that takes in the tree to process, doesn't take in takes in an element as a parameter, and then mutates and is now processed itself to put that element into the tree at the right spot. And you're correct, that is what this is supposed to do. However, right, and so normally a mutating operation like this we would expect to have void return type, right? So in order to show us that, hey, this method mutates the thing that you called on, right? But here we don't do that. We return a instance of being a binary search tree. The reason why we need to do this is related to that empty tree idea, right? Remember, at the very, very bottom of our tree, at the leaves, we're going to have empty trees. So just like we had empty binary trees, we're going to have BSTs with empty BSTs and non-empty BSTs. So the empty BST, the problem here is that when you insert an element into an empty BST, that's not an unsupported operation. That should work. What should happen is this empty BST should say, oh, I don't have any elements, right? I don't have any values. I'm an empty BST. And you want to insert a new value into an empty BST. If you work out the axiom, we know exactly what that's supposed to produce. That's produce the same thing as creating a non-empty BS tree, right, with 2 empty trees as its children, a leaf, right? A tree with 1 item in it, right? I started with a tree with 0 items in it. I inserted an item. I should end up with a tree with 1 item in it. But the problem is I can't make an empty BST a non-empty BST. It's already an empty BST. It's kind of set in stone as an empty BST. So I need to be able to turn an empty BST into a non-empty one. The same thing happens with remove. If you have a BST that only has 1 node in it, that's a non-empty BST. And if I remove that element that's at the root of that non-empty BST, I should end up with an empty tree. And so there are edge cases for insert and remove that require the result to be a completely different type of what you started with. And so just mutating the thing you have won't work. So in this case, you can mutate, right? So if you're just a non-empty BST, if you're not at the top or at the very bottom, and you insert or remove, you can just change yourself, right? And that's fine, right? And that's good, right? That's exactly how it's supposed to work, right? So, but somehow we have to communicate the results, right? Which could change objects. An empty BST could turn into a non-empty one, and vice versa. And then a lot of non-empty BSTs won't change. So instead of making this a void method, we have it return a value. But that means when you call that method on a tree, the thing you get back out might not be the thing you started with. So you have to reset any main variable back to the result. So in other words, let's see if I have it on the slide. I thought I did. Right. When you want to call and recurse if you're trying to recursively insert into one of your children, then you can do that by calling insert on your child, right? But then the result, you have to reset your child to be whatever it produced as a result of that. It might be the same object, right? That's okay. So it's okay to just reset it to the same value, but it might be a different kind of object altogether, and so that's why you have to do it this way. So that's the one tricky bit about the implementation for A5, but otherwise it should hopefully be relatively straightforward, right? All right. Now there is, so I have a couple of hints and notes about inserting and removing. So this is also again about A5, right? When you want to insert a value, this is a lot like contains, right? You compare the element to the value at the root, right? If it's smaller, right, or equal, actually it turns out equal, it doesn't really matter. If the value you're trying to insert is smaller than the one that you have at the top of your tree, at the root, then you simply insert into your left. And that works, right? Because your invariants are still hold. Like we can look at the invariants and know that, aha, that is the correct way to deal with this, right? I'm trying to insert into this tree, right? The invariant is everything in my left is smaller than what I have here, and everything in my right is larger than what I have here. And I did this the wrong way. So I compare. This is smaller. It goes left, right? But I keep going left and right the wrong way. But I'm saying the right thing, right? If it's larger, it goes right, right? And that's easy, right? Until we get to until we get to a spot where left is empty, or that's gonna be beautiful. Yeah, that's right. That's why we do the empty tree, because that's all we need to do. We can recurse, because it turns out inserting on an empty tree is well defined, and so it will work just fine. You'll get all the way to some spot where the direction you're trying to go is empty, and when you ask to insert on an empty tree, it's going to replace itself with a non-empty tree, which is a leaf. Isn't that just beautiful? I love that. Right. Remove is a little trickier, okay? So again, it's recursive. If it's smaller, right, then try to remove the element on the left-hand side, because that's where it must be. If it's larger, do it on the right-hand side. But if it's equal, if it's here, if it's at the root, things get tricky, because I have children to think about. I need to have something here, right? But it has to maintain those invariants, and what am I going to do, right? So the trick is to steal from your children, okay? So if you are, do this all the time, right? Like, come on, I'm Gen X, dude. We bankrupted you. I am sayonara in like 25 years, and you guys got tsunamis coming. Anyway, so, right, so that was pretty insensitive. I'm sorry, right? But you think we're the slacker generation. We are just really, really angry. Like, you put Primus on and get a whole bunch of Gen Xers in a room, and things will get broken. So, right. So, the idea here is, let's say we're trying to remove. Let's say we're trying to remove an element, and that element is at a place where it's, we find the element, like we recurse, then we find a node where we found that element. So we're removing 4 here, right? So we're at that 4, we're trying to do the recursive call, remove 4 there, and at that point, if you are any sort of leaf, right, or a leaf or somebody that, or a node that has one side that's empty, right, it's an easy removal. Because if you're a leaf, right, if you have no children, then removing here just turns into an empty tree. And you just return an empty tree. Oh, you removed me, I have no children, I have no reason to exist, I'm an empty tree, right? Right, and so that's, and if you just have one kid, you just use your kid as your replacement, right? You say, I have a left but no right, I need to go away, here, take left. He'll be your child, right? Or the other way around, right? Sophie's choice, right? You only have one. I guess we haven't made a Sophie's choice yet, right? So, there's you remove, right? If we remove an element of a non-empty tree, right? Now we have a non-empty tree with 2 children, right? So now we have no easy way to do this, right? We again steal a child, right? So what we do is we ask our right-hand side, what is your smallest element? And that's, that's find min, right? That is something that's defined there. And it will find that smallest element, and it will return it to me. And I replace the element I'm trying to remove with the smallest element, that I found in my right? And then I tell right, hey, go remove, your smallest element, right? I know what it is, you just gave it to me, and now I'm going to turn around and tell right, go remove that element. And so we know that element, if it's the smallest element of right, makes the invariants all hold up, right? I took something that was the smallest member of my right tree, and I installed it at the top of my tree. Everything on my right was already everything bigger than everything on my left, so the invariant that what I installed at the top is still bigger than everything on my left still holds, right? And everything on the right is, because this was the smallest thing on my right, then even if there are things that are just as small, there's certainly nothing smaller than the smallest thing on my right. And so everything on my right is still bigger than what's at the top. And then I take away that smallest thing from my right to account for the fact that it moved. Right. Okay. It turns out that the depth of a BST tree is going to depend on the order of the inserts, right? If I insert 1, 2, 3, 4, 5, 6, 7, 9, or 1, 2, 3, no 4, I don't know why, 5, 6, 7, 9, right? Then since they're in order, they keep going right, and I end up with essentially a linked list and no tree structure at all and a height of 6. But the same set of elements inserted in a slightly different order will give me a bushier looking tree, right? And here my tree is more balanced. It turns out the height of a tree is a key component in how well it does in terms of performance. And we'll see that in a second, right? If you have a completely balanced binary tree that is completely filled out, there is a formula for how many nodes are in such a tree, and that is 2 to the height of, of the tree plus of the tree plus 1 minus 1, right? So if you have a 0 height, right? If you're just one node with 2 empty trees underneath you, that means you just have one non-empty node. Then 2 to the 0 plus 1 is 2, and then minus 1 is 1. You have one node. Totally works, right? And so on and so forth. And you should be able to see this because, right, we have twice as many children each level we go down, and we're just, have this nice exponential function. The performance of a tree of a binary search tree is directly related to that height. Contains in a binary search tree becomes really easy, right? Or not easy, but easier. So if I'm looking for a specific element, I don't have to go to both sides. I can look at the roots, and then I know I either found it, or I can go left, or I can go right, right? So to find something for contains, we don't have to go, usually we won't have to go and visit every node. We'll just have to visit the path from the roots at most to the height, right? The furthest away it could be is the furthest leaf, so the height of the tree, right? And so that's as far as we have to go. If the height of the tree is n, right, if we have a degenerate tree, that sucks. But if we have an average tree, right, so the worst case could be order n, but the average tree, if things are relatively random and we end up with a nice, kind of evenly spread out binary search tree, is going to be log n, right? And that's binary search tree, binary search. Right? Every point we go bigger or smaller. Here, bigger or smaller. Here, bigger or smaller. That's exactly what we did with a sorted array, right? Where we were able to look things up because it was sorted. A binary search tree essentially is storing things in a sorted way, right? So there's always a worst case, but the average case for most operations is order log n, right? Size, if we do it recursively, ask for the left size and the right size, add them together, then add 1. That's an easy recursion for size. Then that's order n because we have to visit everything to count it all up. You can, like the linked list example, right? Store the size explicitly at a node, so you know how big it is with its children. And then every time something inserts, you make sure that goes up, and any time something removes, you make sure that goes down. Right? So you could do that. In that case, you have an order 1 operation. So how do we sort with the BST? Easy. We create an empty one, we put in all the items, and then we retrieve the items in depth first in order search. Right? So, we go down the left side, we go, okay, go to the left, keep going left, we keep going left until we get to the bottom. That's 1, and then there's no children there, and then we come back up, and that's going to be the next biggest, and then we go back down, it's going to be the next biggest. And the reason why is because at every spot we know what the relationship is between nodes to the left and nodes to the right, right? Everything to the left is smaller, everything to the right is bigger. So if I visit everything to the left first, then visit the node I'm at, and then visit everything to the right, I know that I'll get everything in order. And you could go, if you go right to left instead of left to right, then you get everything in reverse order, right? If the average height of your tree is n, right? So how fast can we do this? Well, we have to create the tree, that's order 1. We have to do n insertions, and each insertion, if they're coming in random order, is on average going to be log n. So that's going to give us n log n. And then we have to traverse. And we know that we have to visit every node to traverse, so that's order n as well, right? If I have 3 things in sequence, right? So that's how I'm going to do my sort, right? I take the maximum of those 3 things. The biggest of those 3 function families is n log n. So the overall procedure for sorting with a binary search tree is order n log n, right? The nice thing is that you can get, remember how sorted array, the reason why we want to do that is because we want to sort as we went along, right? Like if you want to sort as you go along, then you have to keep it sorted every time you insert, right? But the problem with doing that with a list was that every insertion was order n, and so overall my work was n squared. With a tree organized this way, we can still have everything sorted as we go along, right? But overall, we only pay n log n price, which is as fast as we could have done if we just had all the data at once and sorted it all at once using quicksort. However, it could go very, very wrong, right? If the order of insertions results in a tree like this, then you're right back to order n squared. which, here it is, it's a linked list, right? You did exactly what we were doing with sorted array, right? Or sorted list. In this case, with the linked version of sorted list, right? This is exactly equivalent. So insertions gone wrong with the binary search tree is pretty much the same thing, right, for this degenerate case as using a list structure to try to maintain a sorted list. How big a difference is that? Pretty damn big, right? Let's say you're doing this with 1 million items, right? Order n squared is 1 million times 1 million. Order n log n is 1 million times 20, okay? And at 1 million operations a second, even if your computer's pretty fast, right? Order n log n takes 20 seconds, not bad. Order n squared is going to take 11.5 days. And that's just with 1 million items. Now, of course, our computers do a lot better than 1 million operations a second, but also our data sets are a lot bigger than 1 million items, right? How many things is Amazon sorting every day? Who knows? All right. One last note about traversals on a binary search tree, right? If 2 binary search trees contain the same elements, it's going to depend on their insertion order, right, for what structure they take. Now, 2 binary search trees that were the result of the same sequence of insertions will be the same binary search tree. We can prove that axiomatically, right? But 2 different orderings will result in a binary search tree that has 2 different shapes. And because of that, right, even though we can traverse either one in order and get exactly the same sequence of things out, right? That's not going to be the case for a pre-order traversal or a post-order traversal. The only depth-first traversals that are going to be guaranteed to be the same on all binary search trees that contain the same elements, no matter how they were inserted, right, is going to be a in-order depth-first traversal, going to everything on your left, then where you are, and then everything on your right, right? Because right, all the other traversals, the other 2 depth-first traversals and breadth-first, depend on the structure, like where the nodes are. And we can have different structures of the same set of elements in a binary search tree, depending on the order of the insertions. All right. We are going to end 15 minutes early. So before everyone leaves, is there any questions? Did anything come up that wasn't explained? Assignment 5, if you look at the coded assignment 5, I've already done the empty binary search tree, okay? So that is already done. So that implementation is done. You can use it. The binary search tree implementation has some things done, right? The fields are declared, the constructor is there, some easy things are done, but the ones that are different from binary search, like size, insert, remove, etc., some of those aren't done, but you should be able to, given the notes that we have today, come up with reasonably straightforward kind of solutions to it. If this is taking you more than, I would say, 2 hours, right? Then yeah, you know what? Send me email, or not send me email. Don't send me email. Don't. But you might want to consider going to office hours or to the cohort, or otherwise talking to some peers. It's meant to be pretty straightforward if you understood today's notes.